No tail, a glow aimed straight at the sun, and a path through our solar system that doesn't fit any random chance. ESA's newest image of 3I/A TLAS reveals something no comet watcher expected. Instead of the vaporous plume every textbook promises, here is a hardened core, blazing in defiance of cosmic rules and moving as if on a mission past Mars and toward Jupiter. If this is just a comet, it's rewriting the manual on what comets can do. But if it's not, the stakes escalate fast. A visitor behaving less like a wandering rock and more like a relic, or a probe. And what comes next if explanation fails? October 2025. The ExoMars Trace Gas Orbiter points its KSSS camera at a faint visitor threading through the Martian sky. Over several nights, the instrument team collects a sequence of 5-second exposures, unusually long for a spacecraft built to image the rust-red surface of Mars, not the blackness beyond. Each raw frame captures a tiny, fuzzy dot against a field of pinpoint stars. The comet's core, although unresolved, is clearly broader than any star in the field. That difference, twice the width of the stellar point spread function, signals the presence of a compact coma, even if the nucleus itself remains hidden inside. To make sense of such faint signals, the team turns to stacking. Dozens of images, each cleaned for cosmic ray hits and background noise, are aligned on the predicted motion of 3I/Atlas. Median stacking suppresses artifacts, while calibration files, bias, dark, and flat frames correct for instrument quirks. The result? A sharpened composite where the comet's core stands out, surrounded by a faint envelope, but with no sign of a classic tail. Photometric analysis confirms that the observed width is not just a trick of optics or motion blur. The stars remain tight points. Only the comet shows this subtle spread. Every step is checked. Astrometric reference stars anchor the field. Exposure logs and spacecraft attitude data are matched to the predicted path. The team cross-compares against known imaging artifacts, searching for telltale streaks or cosmic ray ghosts. None appear in the stacked product. The comet's image is steady and real. Yet, for all the care, the nucleus itself cannot be separated from the surrounding haze. The resolution limit of KCSIS at 30 million kilometers means the core remains a mystery, quantified only as unresolved but extended. Raw and calibration frames, while essential for forensic validation, are not always released with the first public data. Formal requests, sometimes even Freedom of Information filings, are needed to access the full stack. For now, the world sees a sharp, bright core with a faint, sunward glow. The textbook comet tail is missing. Other Mars-based instruments, like Mars Express, struggle to detect anything at all. Their shorter exposures and different cameras barely register a blip. No direct detection, only hints in the noise. ESA's release policy favors rapid public access, but processed stacks and calibration products often remain behind team doors until analyses are complete. The scientific community waits, eager for raw frames and full transparency. Without them, the boundary between signal and artifact remains a matter of trust and protocol. What's left is a dataset that demands caution. The core is sharp, the coma is real, and the absence of a tail is not an illusion. But definitive answers about size, structure, and true nature still depend on data locked behind administrative doors, waiting for the next round of scrutiny. Comets, by design, are ruled by sunlight. As they sweep into the inner solar system, ice locked away for eons begins to boil off. This process, called outgassing, drives jets of gas and dust into space. But the direction of these jets isn't random. The sun, emitting a constant stream of photons and charged particles, acts like a relentless wind. Radiation pressure, the physical push of sunlight itself, and the solar wind, a flow of charged particles, both shove material away from the sun. The result is a textbook rule. Comet tails always point away from our star, no matter which way the comet is actually traveling. Imagine a garden hose spraying water. If you aim the nozzle toward a fan, the spray bends away from the wind. Comet tails behave the same way. The dust tail, made of fine grains, responds most strongly to sunlight's push, fanning out in a broad, pale arc. The gas tail, shaped by the solar wind's magnetic field, often forms a sharper, blue-tinged streamer. Both tails are anti-solar, opposite the sun, because that's where the physics sends them. This isn't just theory. Every comet catalogued for centuries, from Halley's famous return to the recent interstellar visitor 2I/Borisov, has followed this rule. Even when a comet rounds the sun and reverses course, its tail flips direction, always keeping its back to the solar glare. The orientation of the tail acts as a compass needle, telling astronomers exactly where the sun is, even if it's out of frame. The details can get subtle. Outbursts, rotation, and jets from specific vents on the surface can create kinks or knots in the tail. But the dominant force remains the same. Sunlight and solar wind dictate the flow. When a comet's activity ramps up, the tail grows longer and brighter, always streaming away from the sun. If a tail points anywhere else, especially toward the sun, it's a violation of the most basic expectation in cometary science. This is why astronomers pay close attention to the direction and shape of a comet's tail. It's not just a pretty feature, it's a direct probe of the physics at play. The anti-solar tail is so fundamental that any deviation immediately raises eyebrows. When an object like 3I/Atlas breaks this rule, it's not a minor oddity. It's a challenge to the entire framework that defines what a comet is and how it behaves under the sun's influence. 3I/Atlas hurtles through the solar system at nearly 130,000 miles per hour, a speed that places it far outside the gravitational grip of the sun. Its path, however, is what has orbital dynamics experts recalculating their models. Instead of plunging in from a random, steep angle, as most interstellar visitors do, 3I/Atlas arrives almost precisely along the ecliptic, the flat plane where the major planets orbit. This is not just a geometric curiosity. The odds of an object from deep space threading itself into the solar system's disk, rather than slicing through from above or below, are vanishingly small. Some specialists estimate less than a 1% chance, though no peer-reviewed simulation has yet pinned down the true frequency. The intrigue deepens with the sequence of planetary encounters. After entering on the ecliptic, 3I/Atlas passes near Mars. Weeks later, it swings close to Jupiter, two gravitational giants in a near-perfect alignment for what spacecraft engineers call a gravity assist. This maneuver, familiar from decades of planetary exploration, lets a probe steal a sliver of momentum from a planet, bending its path and boosting its speed. For a comet, such an orchestrated sequence is rare. For an interstellar object, it's almost unheard of. Dynamics teams have begun running Monte Carlo simulations to test whether this choreography could be a cosmic accident. So far, all that's clear is the rarity. Random interstellar objects, modeled as entering from all directions, should only infrequently align with the ecliptic, and even fewer should thread the needle between two major planets in rapid succession. Previous interstellar visitors, Oumuamua in 2017, Borisov in 2019, followed more typical, steeply inclined paths, never flirting with planetary assists. 3I/Atlas's trajectory stands apart. Some argue this is a statistical fluke, the sort of 1 in 10,000 event that becomes inevitable when billions of objects cross billions of years. Others see a pattern that hints at intent, if not by design, then at least by some unknown dynamical process. The absence of a published probability keeps the debate open, but the sequence of moves, ecliptic entry, Mars pass, Jupiter approach, reads less like the path of a wandering snowball and more like a mission plan. For now, the numbers are missing, but the questions are multiplying. Thermal modelers expected a fragile wanderer battered by eons in deep space. Instead, the numbers from Hubble, JWST, and Mars-orbiting images point to a nucleus at least 3 miles wide, possibly more. That's not just large for an interstellar visitor, it's a behemoth by comet standards, rivaling some of the biggest solar system comets ever measured. Survival at this scale demands more than luck. Most smaller bodies would have been eroded to dust by cosmic rays and micrometeorites long before reaching our neighborhood. Yet here sits 3 I/ATLAS intact, its core hidden beneath a tight, unresolved haze. Spectroscopists searching for clues in the faint light found something stranger still. The optical spectra, pulled from Keck and VLT data, show strong nickel emission lines, clean, sharp, and unmistakable. But iron, the usual partner in comet chemistry, is missing. Not just faint, absent. The detection limit for iron is 10 times lower than the nickel signal, yet no trace appears. In solar system comets, iron outshines nickel by orders of magnitude. Here, that ratio is flipped on its head. Some propose the nickel is locked in metal-organic complexes, or that iron is trapped in dust grains too big to vaporize. Others wonder if the material itself was forged in an environment unlike any known comet nursery. The molecular story adds another layer. JWST's near-infrared spectra reveal both water and carbon dioxide, but in a ratio that breaks the rules. The CO2 to H2O line fit lands at 0.57, nearly double the solar system average. Most comets lose water as they approach the sun, with CO2 trailing far behind. Here, carbon dioxide is almost keeping pace, suggesting either a different ice mixture or a formation history in a colder, more volatile-rich region. Some laboratory analogs hint at similar chemistry in carbonaceous chondrites, but nothing matches the full signature. Polarimetry, the subtle science of measuring light's orientation, offers yet another anomaly. The coma's negative polarization minimum, measured at -2.7%, is deeper than typical comets, with a low inversion angle. Only highly porous, magnesium silicate grains mixed with ice fit the models. This dust is darker, fluffier, and more complex than the textbook comet tail. Each finding adds to the sense that 3 I/ATLAS is not just a statistical outlier, but a physical one. Big, tough, and chemically out of place. The evidence, piece by piece, refuses to settle into any familiar pattern. HiRISE, the high-resolution camera aboard NASA's Mars Reconnaissance Orbiter, was scheduled to capture 3 I/Atlas during its closest Martian approach. The observation window was tight, just a few days in early October 2025, yet the operation unfolded under the shadow of a US government shutdown. Data processing and public release ground to a halt. Images, if acquired, were routed through a backlog, locked behind administrative barriers. The mission's operations lead described the situation as frustrating but not unprecedented, pointing to the strict protocols that govern planetary data, especially when the agency's funding lapses. Into this void, rumor rushed in. Forums and social media channels speculated wildly. Had HiRISE seen something so extraordinary it required vetting by higher-ups? Or was the delay just another casualty of bureaucracy? Unverified claims spread, some alleging internal debate over what the images showed, others suggesting technical glitches or even deliberate suppression. The absence of official updates only fueled the fire. Viral posts recycled old images, spliced with speculative overlays, creating a feedback loop of anticipation and suspicion. Meanwhile, the science teams waited. HiRISE, built for surface mapping, pushes its limits when targeting faint, fast-moving objects like 3 I/Atlas. Each frame demands careful calibration, dark frames, flat fields, and precise timing. Without access to the raw data and full calibration products, outside experts could only guess at what the camera might have captured. Calls for transparency grew louder, echoing through both professional circles and the wider public. The lesson was clear. When data is withheld, even for procedural reasons, the narrative slips beyond the control of those closest to the facts. Scientists are not short on theories, but the weight of evidence must be measured, not just imagined. Avi Loeb, a Harvard astrophysicist known for challenging orthodoxy, has suggested that when multiple independent anomalies converge, strange chemistry, sunward coma, a trajectory resembling a flight plan, the probability of a non-natural origin rises above background noise. He's spoken publicly about a 30 to 40% prior probability for artificiality, not as a calculation, but as a heuristic to keep the door open. The scientific community, for its part, insists that such numbers remain personal estimates unless grounded in formal analysis. No peer-reviewed paper or official report assigns a figure to the odds that 3I/Atlas is engineered. What matters more than any single claim is the running scorecard. Each hypothesis, standard comet, ancient probe, technological relic, automated scout, makes testable predictions. The null model expects a classic comet, random orbit, anti-solar tail, familiar volatile ratios, iron outshining nickel. A probe or relic should show deliberate trajectory, non-volatile chemistry, or metallic signatures that don't fit natural formation. A beacon or time capsule might broadcast non-random signals or display engineered isotopic ratios. These are not just labels, but working hypotheses, each with potential falsifiers. If the next round of spectra finds iron hiding in the coma, or if high-res imaging reveals a fractured, ice-rich surface, the case for the extraordinary collapses. If, instead, the anomalies multiply, if the gravity assist-like path holds up under simulation, if the nickel-to-iron ratio remains inverted, if polarization signals resist cometary models, the probability grid must update. As Loeb and his critics agree, extraordinary claims demand extraordinary evidence, and every new data point either strengthens or weakens the case. The challenge is to keep the grid honest, letting the evidence, not the headlines, decide what story 3I/Atlas is really telling. Protocols for handling interstellar visitors have never felt more urgent. In Vienna, the United Nations Committee on the Peaceful Uses of Outer Space debates a rapid response framework, one that would trigger coordinated observation and risk assessment the moment a new object is confirmed. The proposal calls for automatic data sharing, fast-tracked telescope access, and a standing panel to review biosafety and planetary protection questions. No treaty exists yet, but the pressure is mounting. For 3I/Atlas, the scientific checklist is clear. High-resolution imaging, ideally from both ground and orbit, could finally resolve the nucleus, revealing surface features or possible artificial structure. Metal spectroscopy, especially in the ultraviolet and near-infrared, would pin down the nickel-to-iron ratio and search for signatures beyond natural chemistry. Expanded polarimetry, across multiple phase angles, can refine models of dust grain structure and composition. Thermal mapping, using space-based infrared sensors, may expose heat patterns that tell whether the core is solid, fractured, or layered with exotic material. Precision astrometry, tracking every subtle shift in the object's path, could reveal non-gravitational forces or even controlled motion. Each of these data streams has a dual purpose: to test the null hypothesis of a natural comet and to hunt for the fingerprints of something engineered. The international community faces a choice: wait for anomalies to pile up, or build a protocol that lets evidence speak first. The next interstellar visitor may arrive without warning. For now, the call is simple: demand open data, support global coordination, and follow the evidence wherever it leads. Yet crucial high-resolution images from Mars orbit remain unreleased, and the true source of several anomalies is still unverified. Calls for transparent, rapid international protocols now echo across the scientific community as the evidence demands further scrutiny. For now, the record shows that 3I/Atlas does not fit known natural categories, leaving its origin an open question and its study a priority for future missions.